Are we recording?
Yes. Do you want to start?
Sure. Yeah. Hey, folks. Great to meet everyone. Thanks again for participating in the challenge. So I'm Joe. I'm from Facebook. I'm the product manager for PyTorch, and I think this is something we love to do. We love to work with the community. We love to collaborate around the project, and I think one of the motivations that Gaurav and Christian and Wu and I and others at Facebook, when we started working with YH on the challenge, we wanted to see what we could learn from you, what cool things you could do, how you could improve some of these models. And so, yeah, we're pretty excited to kind of have a chat with you guys and just learn from you, see what worked, see what didn't work, and just, yeah, compare notes. Gaurav, you want to say anything?
Yes, thank you. Hi, everyone. My name is Gaurav. I am part of the PyTorch mobile team and super excited to be here with all of you. Thank you so much for participating in this challenge. Excited to see some of your solutions, how you actually managed to improve the accuracy as well as the power performance. It was given as a sample solution, but it did definitely come from some of the researchers at Facebook. So glad to see the level of enthusiasm and how you improved on that. I would like to also hear from some of you as to how your experience has been, what the community is saying about PyTorch, and where we might collaborate and improve further. And look forward to your continued interest in PyTorch going forward. Thank you.
Hi, this is Christian. I'll jump in here. So I'm the product manager also for PyTorch on device. And thank you everybody for your participation. I know we're really excited with this competition and the outcome of it. And so one thing I think I'd love to hear today is if you can share with us your story in a way and how you got about to developing these solutions. That's something I know we're keen on. But also, I'd like to hear if you have any questions for PyTorch Mobile specifically, or whether it's requests or things you've been wondering, if we can help kind of share a little bit what we've been thinking about and how we're looking at these things. So let us know. Yeah. Thank you.
David, you want to say something?
Sure. I'm David. I'm the tech lead for PyTorch Mobile. I think the others covered it pretty well. I guess I would just say that for myself, the stuff that I'm personally most interested in is any improvements that we can make to the PyTorch framework or the PyTorch documentation to help everyone have an easier time getting the kind of results that you did in this competition.
All right. I think that's everybody from Facebook, right? Did I miss anyone? Okay, I assume nobody wants to hear from Purdue. So let's ask the first prize winner. It's all yours. Do you want to share screen or anything, or you just want to talk? It's up to you.
Hello, everyone. Yeah, maybe I'm the first prize team. My name is Xuefeng. Yeah, well, yeah. Hello, everyone. My name is Xuefeng. We come from China. We come from the company of ByteDance. Yeah. Thank you the organization to organize this challenge. Okay. For this challenge, is very particle. So team sorry about my English. Okay. Pay so much time on this challenge. Yeah. So for this challenge, I want to say maybe some key point. Well, I think some key point is very important for this challenge to win. Yeah. I think the first one is because this the solution will be around the embedded device. I think the first important thing is about the video decoder. Yeah, this is the most important thing. The first thing I think I want to say. Yeah, because the input file is MP4 video, we need to decode that into a battery. Yeah, this is maybe the most important thing. The second thing is how to get the keyframe from the video, because that video maybe have the 3 minutes, about 180 second. But each second has 13 frame. Maybe it contain about 5,000 picture frame, but the keyframe only have about 100. How can we get the keyframe from this 5,000 image? I think the second the key point from this. The first second key point is the OCR technique, the object detection and text recognition technique to recognize the text from the image. Yeah. The last second is to process the video result. Then we can concate the result to return the best answers. Yeah. Maybe I think this is the 5 key point of this challenge. Any detail do you want to know from these 5 key points?
So were you saying that from the video, you only processed certain keyframes?
Yeah.
And
yeah,
were those, go ahead.
Do you want to know how do we get the keyframe?
Sure.
Yeah.
Yes.
maybe the frame is there have the I say for 3 minutes videos, it maybe contain about 5,000 pictures. Yeah, maybe the first way you use a simple way. This first simple way is to have separate. Maybe we can separate the image about 7 or 10 each frame. Yeah, this is the first one. Then we'll use the optic flow. Yeah, to get whether the frame is not move. We'll use the optic flow to judge, because the right answers what the keyframe is still don't move. So we'll use the optic flow to judge whether this frame is still don't move. Maybe we'll use but because it run the solution in the embedded way. So we'll use some very faster way to do this. Well, the actual way we do this is use the dense optical flow. Yeah. Maybe we'll use the 2 threshold to deal with the dense optical flow. Then to judge whether this frame is not moved. Then maybe we can, but we also need to keep the record. We must need all of the keyframe must be recorded. Use this frame keyframe the extract algorithm.
So you used optical flow to find the frames that were not moving, and
yes.
Then you ran OCR on those frames?
Yes.
Did you use a library? Oh, go ahead.
Well, only use the OpenCV to calculate the optical flow. We don't use any the 3-part operator, but 3-part operator is OpenCV.
Got it. And then what about the OCR? Did you use the same model from the sample solution for OCR, or did you train your own model?
We train our model for the OCR. Maybe it can be dive into two sub problem. The first one is the text detection. The second one is the text recognition. For the text detection, we'll use the segmentation based methods to do the test the object of detection, because maybe we think for the detection method, maybe have the two way. The first way is the regression based method, just like one stage or two stage, or maybe this way. Maybe there are so many methods, but we use some do the current in regular case for the text detection. The method paper where we reference is the PSE-LET. This is maybe a CVPR 218 years. Yeah, CVPR papers. There is a PSE-LET. We're based on this method to do the text the detection. Maybe I think it's very fast. Yeah, but and also for the network structure for the PSE, maybe we'll do some because the architecture is based on the deployed device. So maybe we'll try to run the network on the Raspberry Pi. Then we'll load the HTML time, so it help us to redesign the network. Then can help me to get the better speed and accuracy. This is for the object detection, the test detection. Maybe for text recognition, maybe we don't say the Facebook models. We'll train our model by ourselves. For text recognition, they also have many ways. Best as you say, use add STM at CTC, maybe say at CTC, maybe someone use CTC, and maybe someone use transformer to do this text recognition. We'll use the most faster way. We only use the CN at CTC to do this the text recognition. Maybe so we also can achieve a lot good recognition accuracy. Yeah.
A quick follow-up question actually on the testing part. It sounds like, so you have these building blocks for your solution, and so each of them you're looking at measuring the performance and the power. Is that correct? You measured it at each level independently. Okay. And then, do you have any tools that you were using for that, for these measurements, for whether it's power, accuracy, anything you?
Okay. Maybe in the beginning we want to use some meter to testing the power, but we find we only use the time. Use the time because the power is the current U I and plus T. Yeah, we only measure the actual time running on the device. Maybe it's a very simple way to measure the power. I think they only use the time. We think the U and I is not changed. Maybe we only can calculate the time, so we can load the actually power. So yeah, we only use.
Got it. So time was the proxy. Yeah. Okay. Perfect.
Yeah.
Any part of your workflow that took more time, or that you wanted to see improvements on?
Okay, but as we think the first I think in the beginning we want to improve the whole pipeline. Maybe I think the video decoder maybe is very fast, very slow, Yeah, maybe in the the organization, the organization, they use the system. We find that it can use the hard decoder to hard decoder. We can use the system API to do the hard decoder for this MP3 file. Maybe the piece is H.264 format. They will use the FMEG pack to do the hard decoder. But later, the organization changed another system. We found we cannot use the hard way to decode the image. Maybe we only use but so we have to use the Levy, the OpenCV video decoder way to do this. But we also try some where in the beginning in the first system, Raspberry Pi system, we use we use C++ code to write this video decoder. But finally, it cannot use in the later Raspberry Pi system. This is the first one we think is very slow. The second one is the keyframe. The keyframe extract, because we need to do each frame. We also need to do the object flow for we sampled. But for OCR, we only do maybe have the 5,000 image. Where if you use you separate just, for example, we use 5, maybe we only do to calculate 1,000 image the object flow. That's object flow. But maybe we can just try about 100 image. So you need to calculate object flow for 1,000 image, but you need the time you need to deal with the OCR. You only need to deal with about 100, maybe not except the 200 image, because the image. So we think the way and to extract the keyframe is also very time consuming. The second part is the OCR. This is the absolutely will take time. But I think the OCR is also take time. But in the first beginning, we think the may come to, maybe for the people they always think the OCR detection and recognition will take the most time. But the second video decoder and the keyframe extractor is also very time consuming. Maybe we're not maybe and very detailed each part the time occupied. Maybe we think the how to be maybe the OCR part maybe 30%. Maybe we are not test maybe we are not test each part. We only take it at the whole system to test the time.
So thank you for sharing that. So I want to make sure we have some time also to cover some of the other winners. So do you have any other questions otherwise for that team? We can also come back later.
The question for PyTorch or other question?
So actually, let's first hear the story from the other two teams, and then after that, let's open up for the questions for PyTorch, if that's okay.
Okay, perfect.
YH, I'll let you drive for the next team, the intro.
Okay, well, I think I thought Joe is going to lead the discussion. Joe, do you want to
take
over?
I mean, Christian was doing a good job.
I can.
So, yeah, go for it, Christian. I mean, you're the mobile PM if you want to.
Sorry, I don't have all my notes here. So would one of the other two teams present? I don't have all the names showing up here. Sorry.
I got. Yeah, I can send you a. So we can hear from Texas A&M.
Yeah, thanks.
Who wants to speak from Texas A&M?
Hello everyone. Sorry, I don't plan to put a video on because our internet bandwidth is limited. So I would like to save the bandwidth for my voice. Sorry about that. Let me share a screen. We made a simple slide to introduce our solution. Let me share again. some technical issue. Okay, can you guys see the slides?
Yes, yeah.
Okay, great, great. Thank you so much. First, let's introduce our team. We are we are a collaborative team between industry and academia. The industry is the Quais AI Lab from Seattle, and academia is Texas A&M student, Texas A&M University. So this is a big picture of our solution. It is composed of different stages. The first one is definitely data collection. And we try to collect some data in our building, in our building on campus, because you don't have training data released. So we build our own platform with some drones and some operators, and we collect some data, and we developed semi-supervised data annotation, and we which borrows some strategies from image registration that is able to almost freely annotate the bounding boxes with text within one scene. And in that case, we only need to annotate the first frame, and the remaining frames can be, the annotation on the remaining frames in the same scene can be freely obtained. Okay, this is the first stage, which is data collection. And the second stage is actually composed of 3 substages. The first substage is we segment the videos into different independent scenes. And like the first prize winner has shared, the key here is to find the key frame, because there are millions of frames I mean, maybe not millions, at least hundreds, thousands of frames in a given video of like 5 minutes length. We do not need to run our algorithm on every frame. We only need to find the keyframes. And for in ideal case, we just find one frame, which is the best quality frame in one given scene. So the first substage is we want to segment the videos into independent scenes, and so that we can just select the best quality frame from the independent scenes. And when we, of course, many times we are unlucky and we get some low quality frames that with strong blurry or low light or glare, these kind of artifacts. So we need some strategies to figure out, to do a binary classification, whether the selected frames is low quality or high quality. We use a strategy from, it's a NIQE, which is a quite old one. If you know, it's Alan Bolwick in UT Austin. It's invented by him. So we use this NIQE to do a binary classification on whether the selected image is low quality or high quality. And here we don't quite care about whether it is blur or glary or low light. We take all these together, and if our image has any of these like artifacts, we treat it as a low quality one. And the last substage is cropping the text-oriented regions. Here is to improve the signal noise ratio. I mean, like given a frame, usually the text region is not in the center or not occupying the major, the most portion. So the point here is to crop this out so that in the frame, the text, so that we can improve the signal noise ratio by making the text occupying the main frame. And also, this gives us 2 benefits. The first is increase signal noise ratio, which improve the recognition performance. The second is actually we are getting rid of those unrelated pixels, and it saves us energy when we do convolution on the whole images. Okay, we are done with the first 2 stages. And and the third stage is image enhancement. For some images, we just run some enhancement algorithm to improve the image quality. And the fourth stage, which is video text spotting, we use a false model. Actually, we build our own model, but it is greatly inspired with from false, and it will be introduced later. So that model is actually a two-stage end-to-end text spotting model, which starts from the backbone, then comes to detection, which detect those bounding boxes. The last stage is the last component would be the text recognition or OCR model, and the last stage is model compression plus deployment. In the compression part, we only tried 8 points quantization, and we found that quantization over training works best, and also pruning is very important. And pruning, and every time we prune the model, we always fine tune on the on the training data to guarantee the performance can be saved back. And the very last one is deployment. We just use a PyTorch given QMPAC, and thanks PyTorch team, your given QMPAC is very powerful and easy to use, and we appreciate it. Yeah, so I've given our big image, and I would like to let my two members to briefly introduce their own work.
Can
So John,
you start first about the stuff you covered so far?
Sorry, can you say the question again, please?
Can I first ask a few questions about the stuff that you already covered?
Cover? I'm sorry.
Can I ask a few questions about this?
Can we ask some questions? Yep.
So pruning in this case, does that mean like you would train partway and then drop some channels and then train some more?
Oh, yes, correct. And
then,
only do. Yes.
Go ahead.
Mm-hmm. Yes, actually, we only do structured pruning here, that we reduce the channel width. It's kind of like knowledge distillation, and we don't change the whole architecture, but in each filter, we try to reduce the number of channels. And we empirically found that the given false model based on ResNet backbone can be greatly reduced some stages. At least some channels can be cut to even 1/5 or 1/6 of the original number of channels. So pruning here plays an important role here.
And then the other question I had was about QNNPAC. Did you make any calls to QNNPAC directly or make any changes to QNNPAC, or were you using it through the normal PyTorch quantized APIs?
We just use the normal APIs, and it has many hyperparameters. We just tune with the parameters. We don't change much, just borrowing using the APIs. Okay,
great. Thanks a lot.
Yeah,
hey,
thank you.
I had a quick question as well. On the data set you guys generated, I guess this was a fine-tuned model, right? So it was pre-trained, and then you fine-tuned it on the data you collected?
Exactly. We start from pre-train and then do some compression, then fine-tune.
Okay. And you did some data augmentation based on the data you collected as well, or?
Yes, we did data augmentation. Here we use here there are two factors of augmentation. The first is rotation angle, and the second one is multi-scale. And if you do any project in object detection, we found that multi-scale training is very important. Actually, the most difficult part in object detection is small objects. Mm-hmm. Yeah, so multi-scale training and the multi-orientation angle. We use these two factors we add these two factors into our training as data augmentation, and we found they both contribute.
Interesting. Thank you.
Yeah, thank you. Yeah, any more questions? Yeah, I would like to invite my members to collaborators. They will introduce their part, go into detail. So John, could you please open your introduce your work? Thanks.
Thank you very much. Thank you, William, for introducing the pipeline. So I guess everyone has a big picture right now. So the flowchart is about a regular process for the OCR. First, we have the video decoded. We sample images from it. We feed it into detector recognizer. And if its tags are detected, recognized, store it and repeat the process until the video ends. However, this whole process, there's a lot of room for improvements in order to reach remaining high accuracies and low power. Can you go to the next slides, please? First of all, so the detection and recognition part are all built on neural network. However, neural network consumes a lot of power. As a result, my first thought is I want to select the data with a low-level computer vision methods before I reach the detection. Second, as the first team winners said, one of the key methods is to find the key frames because there's a lot of useless frames among the whole video. And they use optical flow, but I use another way. I just adapt it. Instead of having a fixed sample rate, I use adaptive sample rate. So instead of having a 10 or like a 50, I make it like change based on the current frame I have. 3 is, as I said before, the model compression is very important for detection and recognition. That will save a lot of energy. And I also crop and downsample the input image that feeds into detection. And as we can see in the next image shows the diagram which include the selection. The selected here is a bag of low-level computer vision methods that helps to decide whether the image contains text. So now the difference is the sample images, instead of going to detect it directly, I pass it through the selector and it will reject the background images or the extremely heavy blur images before even reaching to the detector and recognizer. So since these methods are all low-level computer vision methods, that helps save a lot of energy. And because by fine-tuning the threshold, we keep this method with a high recall. And besides the selection, another method we have is the adaptive sampling. And here's the diagram that I have the adaptive sampling embedded with the selection. The major workflow remains the same. Instead, we have the sample rate to non-text sample rate, heavy blur sample rate, and clear text sample rate. The whole idea is that I want more clear text images. I want less non-text images and heavy blur images. And for the clear text images, since it's fly by a drone, I'm not sure whether the image I got here, because for the recognition and detection method, even blur images, sometimes it can read. I'm not sure whether that includes the information I need. As a result, I want more clear text images. And in order to get more clear text images, we also have the idea of cache image, which means when we have the recognizer recognize images, I'm not sure whether that's partial image text or whole text. So this time I want a small sample rate so I can get another one to verify. If I get a non-text, which is a background or a heavy blur, I want it to be more aggressively go way forward instead of having a small sample rate. I want to increase it. So that's the whole idea here. And of course, that's a trade-off between time consuming and accuracy, power consumption. So that needs a lot of tuning over here. And for the OCR model selection, for the detection part, we use the EAST model. For the recognition part, we use the CRNN model. And basically, we spend a lot of time on the model compression pipeline. The whole pipeline can be shown very easily in this diagram. We have the pre-trained model. First of all, we fine-tune the model with the sample data set. We prune the model. We fine-tune the mass prune model. We fine-tune the exported prune model again. Finally, we quantize the model and save it to a torch script. And next, my teammate Rahul will introduce the part of his work. Is there any question before that? All right, thank you.
Were there any issues when you exported using torch script? Anything that wasn't expressible in your code?
It's
Yeah, I think when we export, we just export to the using it toward JIT tool, and everything is successful.
Okay.
We don't spend too much time on that. It's because your API is built very well. We just call it and use it.
Awesome. Love to hear that. Cool. Thank you.
Okay. For the data set that as introduced by Zenu, for data set we use the sample videos provided by the organizers, and since we saw that we were using the 5 videos that the organizers had provided, we wanted to annotate the bounding boxes for the text and the text label. And for that purpose, since there were somewhere around 35,000 frames, and we wanted to do it quicker, we came up with an automatic labeling algorithm to just annotate the first frame and use feature matching and homography to annotate the rest of the repeating frames. So this is an example. That is, we use some key points from 2 repeating frames, and then we use homography to translate the bounding boxes from one frame to the other. And yeah, next slide. While we did a literature survey of the text spotting models that were available, and we noticed that most of them were either character based or segmentation based. And since both are either character based, if you go for labeling character annotations, which is expensive, as well as a segmentation which has a complex pipeline which is not real time. So we focused our work on 2 real-time models, that was FOTS and ABCNet. Both these models are single-shot anchor-free convolutional neural network detection framework. And another thing is that they have the convolution shared between the detection and recognition. These 2 things make them real-time models. So we tried both these methods, and ABCNet performed better on cloud, CPU, and GPU. But when we tried to quantize the model, we observed that the FOTS model performed better. And therefore, we went on forward with pruning for optimizing the FOTS model. And we used the FOTS model for, we did quantization and pruning and compression for the FOTS model.
Yeah, thank you all. That's pretty much for our introduction. Do you guys have any questions?
Thank you for the great walkthrough. This is excellent. I don't have any additional questions.
Same here. David, any other questions on your end?
No, thank you. It was great.
Thank you so much. Thank you so much.
Perfect.
Yeah, actually, there are a lot of technical details we didn't go into that much. But if any of you guys are interested, you can just we can schedule a like personal meeting. We can go as much detail as possible if you need. Yeah, thank you so much.
Awesome.
Thank you. Yeah, that's great.
Great detail. Should we move to the last tune? Stony Brook.
Perfect.
Hello?
Yeah, we can hear you.
Okay. Hi, my name is Songwan Chong. I'm a PhD candidate at SRI Korea. Sorry, my cam is unavailable now. I just made really short slide, so let me share with you. Can you see it?
Yep, you can see it.
Okay. I mainly focus on pre-processing and some printing technique. First, I tried to increase the accuracy. After the text detection and recognition process, I cut out the text region by calculating the box coordination. The cropped image gives a better detection performance. So as a result, the accuracy increased, but energy consumption also increased due to the number of inference execution is also increased. So the accuracy is increased to 0.7 to 0.62. Second, I tried to reduce energy consumption. When I visualized every image, I realized there are lots of meaningless frames. For example, an out-of-focus image returned only garbage text. So I applied edge filter to detect blurred image and eliminate the low-scored blurred frames. By applying this pruning technique, the number of inference execution is reduced. For the flat space 01 data case, the number for recognition execution is reduced about 30%. So finally, the energy consumption decreased with acceptable accuracy loss. So the energy consumption is reduced to 0.66, and but the accuracy is quite good as 0.55. And that's all I had. Okay. Is there any questions?
Thank you for the presentation. David, Joe, any questions on your end?
Yeah, so you talked a bit about the pre-processing. For the actual text recognition, how did you do that? Did you use the same model that was in the demo solution, or did you have a different model?
I used the same solution as you gave for the same solution.
Okay, thank you.
All right. If there are no more questions, I think I want to turn it around to the teams if they have any kind of questions or requests or feedback related to PyTorch Mobile specifically that we can try to take in. Yeah, feel free to go right ahead.
Yeah, can you hear me?
Yep, go ahead.
Yeah, maybe maybe we'll have some advice for you to approve the PyTorch mobiles. We found maybe some layer in mobile, just like the depth-wise convolution. This layer, the channel number is equal to the group numbers. For that layer, maybe we found it's not support very well in PyTorch mobile. I don't know. Do you have some other special case for this operation for depth-wise separate convolution? I don't know if there are.
Yeah, so we do use depth-wise convolution in our production models. And so, you know, we've definitely spent some attention to optimize them, but there's certainly cases that we might have missed. So if you have a model or a script that demonstrates this case. If you can send it to us, we'd be happy to take a look at it and try to speed it up.
We maybe think for the just we think just to test the mobile, just some mobile servers. That's mobile V1, mobile V2. You can test this model on your PyTorch model. Maybe you can do some comparison for other mobile inference engine, just like there's so many open source one, just like MNN or NCNN, yeah, Tencent, MNN, and Alibaba MNN. You can do some comparison for the data separate convolution in mobile. Yeah, we think, but we have to test this unit. They are very fast. Maybe you can help. Can you improve the inference speed in the mobile?
Yeah, so we do comparisons like that. Like we internally, two of the ones we look at most frequently are MobileNet v2 and ShuffleNet.
Yeah.
But we're very interested to know like what models other people are using outside of Facebook. So if you want to send us a model that you think is that looks like the sort of thing that you want to run on PyTorch, okay, we can incorporate that into our benchmarking, and maybe we can find some ways to speed it up.
Maybe because the official approved use the FBLET. Maybe FBLET is based on the mobile V2. It's based on mobile V2, but it has a separate WS convolution. So we found this operator is not very fast in the mobile. So we don't use the separate WS convolution. We only use the maybe just like ResNet servers to, because found it very efficient, just like in the current PyTorch version. Yeah, we're just based on ResNet.
So you found ResNet worked better than using depthwise separable convolutions?
Yeah, because I found this layer is very not efficient because the flops is very low for depthwise separate convolution, but the speed maybe is not achieve very good performance, especially for do the quantization. Because quantization is the way we must to do. But after quantization, we found the speed very low, very slow. So we don't use this operation. We only use the normal convolution to this for this.
Okay, so if I understand correctly, you were saying that the depthwise convolution on floating point was slow. Is that right?
The float point maybe is very fast, but we don't test the float point in the mobile areas because we think we must do the quantization. So we don't test the float model. We only test the quantized model in the. Okay.
Well, if you can send us the model that was slow, we can take a look at it and try to figure out how we can run it faster.
Okay, maybe you can only test. Okay. Maybe you can only test mobile. Well, just the model is also based on mobile V2. Yes, maybe you will find it not very efficient. You can profile each layer time. Maybe you can see the depth first convolution of layer time and divide the flops. You can see the calculate the dense. Yeah.
That actually doesn't match my experience because we do benchmark on quantized MobileNet v2 and we get pretty good numbers from it. So
maybe is what you're saying.
Okay.
Is what you're saying is that one of the operators in there that you'd want us to benchmark on operator by operator and see how we're comparing and maybe identify that one within it.
Maybe you can, maybe we're not use the correct testing way. Maybe you can send a demo in the PyTorch mobile website, use the mobile V2. Maybe you can have a demo. We can, maybe we are not use the correct way to test the model.
Yeah, I can do that. Yeah, I'm looking at one of my coworkers did a benchmark on the Samsung Galaxy S8 US version. PyTorch Mobile for MobileNet v2, he got 19.93 milliseconds, TF Lite 18.0 milliseconds, MNN, that's the MNN is Alibaba, I think. 17.
Yeah, Alibaba.
And NCNN, which is Tencent, 27.3 milliseconds. Oh wait, that might have been Float.
Yeah.
Anyway, so we look very competitive. So if you have a model that you're able to send us, that would be great. If not, yeah, we can try like making a script for MobileNet V2 that shows how to get good performance from it.
Okay.
Yeah.
Thank you.
To David's point, like in general for all the teams, if you have like model architectures or external models that are important to you, let us know, because we do want to try to improve performance constantly. And so if we have a sense from the external community what these models are, I think we're keen on learning about that more.
Okay.
Perfect. Okay, any other questions for us or feedback where you can see improvements, things you had a hard time with, or things that were great and everything is perfect? But don't tell us that. I want to know the pain points. I want to know.
Yeah, I know.
I want to know all the headaches that you have with PyTorch Mobile, so
Yeah.
we can go fix them. So you all mentioned some aspects of like pruning and quantization and kind of model compression in general. Around this theme, any piece of feedback specifically of things we can improve, or both in terms of the performance of how that's done, in terms of workflow also? And if not, maybe on the binaries or building it for Raspberry Pi specifically in this case, any issues around that?
Do you have the plan for mobile? For maybe I can ask more question. For the PyTorch Mobile, do you have the plan to support maybe 4 bit to quantization? Maybe the NVIDIA's, maybe their GPUs can support the maybe current the version that can support the 4 bit to do the inference. Maybe they maybe have the CUDA API for batteries. Yes, we think about for some models, the 4 bit it also can achieve a lots of bad accuracy.
David, if you wanna.
Yeah, I am not aware of anyone, at least within Facebook, looking at 4-bit quantization. I heard you say CUDA. Are you talking about NVIDIA GPU like Jetson or something like that?
Yeah, maybe I can look here.
Yeah. The part of the team that I work on, we're focused on like mobile phones, and so like, no mobile phones have NVIDIA GPUs, and so the people that like my team doesn't, we don't really care about NVIDIA, but there might be someone else on another part of the team who's looking at that, but not that I know of.
So is there a need on your end that you see for 4-bit quantization on some of the models you're thinking about?
What? I can look here. Yeah.
Yeah, I was saying, is there a need on your end? Like you mentioned 4-bit quantization, if we're going to support it. Is this something that you're actively looking at supporting on mobile devices somehow? Like
I can ask the question differently.
Yeah.
Can you help us understand why or where you need 4-bit quantization?
Maybe why we need to do the quantization?
No, 4-bit. Why do you need 4-bit?
Oh, 4-bit. Maybe we think for some tasks just like do the classifications, then we'll do the quantization about to 4-bit. Maybe the accuracy is not drop very low, but the speed we can think it can greatly improve the speed. Because if you connect to 4-bit, you use the SIMD instruction to use the assembly language to this. You can 4-bit add 4-bit to 8-bit, maybe 8-bit that's 11-bit. Maybe for most channel you can calculate the on the 16-bit Intel 16. Not use the Intel 33. 32. Maybe we think it's very maybe fast, more fast than 98. Maybe we'll care about the speed.
I think it depends very much on the hardware. So people who are developing custom hardware, I think, are very interested in 4-bit because it's very easy if you're building the hardware to make it support 4-bit very well. But if you're running on commodity hardware like an ARM CPU, it's not so easy. And so a friend of mine knows a lot more about this than I do. A coworker. This is Tolek for anyone who's on the call who knows our org chart. What he told me is that for running on the CPU, if you go more than like 2 to 2.5 bit, then it's very difficult to match the performance of Int 8. But one of the things that we are looking at some point in the future is what we call 16-bit accumulation. So I think this is similar to what you're talking about, where we would still have 8-bit weights and 8-bit activations, but we would adjust the quantization parameters so that we could do some amount of accumulation in 16-bit before we split to 32-bit. And so we could get more of that high performance from accumulating in 16-bit. We're interested in that. We don't have any immediate plans to do that.
Okay, good.
So I think we're running out of time, but I want to make sure that we can still stay connected. And so ultimately, if you have any more follow-up questions for us, you can reach directly to us. I don't know if you have our contact, but I'll make sure with Voyage we connect so we can all sync up. And vice versa. I think what we'll do also is we'll review our notes and chat about it on our end and see if we have any follow-up questions. But this has been very helpful, I know, for me to see like the processes and like how people like broke down the even different steps of the solutions and how they're thinking of optimizing for it. So thank you for participating and thank you for sharing with us all of it. Does anyone have any other follow-up items to cover before we close off?
I wanted to reiterate again, thank you for participating. Thank you for being part of this whole thing. And I know we're looking at what to do for next year for 2021 in the challenge. So if you guys have any really interesting or cool ideas for what we should do in the next challenge, we'd love to hear about them.
Thank you very much.
Thank you.
Thank you.
Thanks, everyone. Bye.
Yeah.
And thanks, White, for setting this up. Appreciate it.
Yeah, thank you.
Ring leader.
Thank you.
All right.
All right. See you later.
Everyone.
Bye.
Be safe.
Thank you for your
Thank you.
Thank you.
Keep safe. Thank you.